Okay, this is the part 2 video podcast for chapter 11 about surface sediment characterization, sampling, and measurement. And what I'd like to do right now is talk about, instead of just the static nature of sediment as we covered it before, what about how sediment changes through time, especially in terms of physical movement? Movement of sediment, of course, it plays a role in terms of changing the volume of space available for water storage. When sediment moves, it changes the hydraulic conductivity of the material. So, if you have an erosion of material and then deposition of fresh material, the deposited material tends to be less compacted and have higher hydraulic conductivity rates, and it can change the habitats that are there. So there's a lot of reasons directly for hydrology as well as for allied sciences as to why we want to know about deposition and erosion of material. So I want to start off on the hill slope and kind of work down from the most aggressive situations to the lowlands where you have relatively finer grained material. So starting of course, so when we want to talk about erosion and deposition, there's going to be a couple of different ways to do this. First is to just measure depths, like how has something changed? It's cut an inch or it's filled in an inch, something like that. We could try to do it volumetrically through mapping methods. We could collect samples and look at the mass balance, like how much mass has come in or left. So those are some of the different things that we can do. And here's just some examples, like deposition of sand in a channel, which could be good or bad, depending on, good for riparian vegetation recruitment, bad if you're the eggs of some fish. Here's a gully that's forming through an agricultural field. So maybe you're a hydrologist and you're studying gully formation and remediation. On a hill slope, a very common thing that we want to know is the ability of Rainsplash to produce sediment or erode it off of a hillside. And if we'd like to isolate just the role of Rainsplash as a mechanism in contrast to sheet wash or rill erosion or gully erosion, then you do that using something called a Rainsplash cup or board. So here is the ground surface, this black line, and on top of that is a tray which has a ring. You can think of this as either like a full circular pan or a rectangular pan so that there's walls all the way around it. And then in the middle of that is a large divider that's going to block the ability of rain to go past that point, as well as sediment to go past that point. So you can see this is on the hill slope, and these little dashed lines are like raindrops that are hitting the ground. Well, when that raindrop impacts the ground, then that can cause a burst of sediment to splash up into the air. And that splash will be in all directions. So we can look at how much of it splashes into the upper side of this pan. And that is what we call the downslope splash, because it's the material that through that energy plus the role of gravity, it's going to be taking that in this downslope direction. On the other hand, behind the divider, we have this protected area, and it's going to be receiving any upslope splash. So this allows us to see individually the downslope and upslope components of splash, and you can take the difference between those two to get the net sediment movement associated with Rainsplash. It's also nice because this gives you a sample that you can then analyze for the properties of the sediment associated with Rainsplash, like grain size distribution. And of course, Rainsplash is going to be influenced by what is the material on the surface, such as being vegetated or unvegetated. So the Rainsplash cup or board is a very effective tool for being able to isolate an individual process and quantify the flux associated with that. Moving up to another spatial scale, not just what's happening in one small area as a function of just one process, but just the totality of what sediment is being produced on a hillside and moving down a strip of hillside, is to build what we call a sediment fence. And this is a schematic, and then I have some photos here. So I'll start with the photos. Typically what this involves is laying out some fabric on the ground, and then having that curved up so that it's on the ground, and it's also creating a barrier to material moving down the hill slope. You can see this is a commonly used technique when we're trying to understand the effects of logging or forest fire, wildfire on sediment production. And here it is a little bit better. So you can see it's dug out a little bit of a so yeah, just this little backfill trench so that it's really tamped down and having the fabric there. And then the sediment is coming down. It gets caught by this silt fence fabric, and that's buttressed by usually wood stakes. But anyway, having that needs to be really strong because you can see from this photo the massive quantity of material that's coming in there. So we're basically just blocking the hillside and catching all of the material that is going by that point. The biggest challenge with this approach is just the sheer labor intensity of it. This is just like backbreaking work when you have this much sediment. So of course, the more often you go in and collect the material, then the less work it's going to be each time. But with a big enough event, it's just, you need to dig out all this material, assess the volume, and then at a minimum, take a representative sample for bulk density so that you can convert from volume to weight. Or you have to dig the whole thing out and just weigh the whole thing. And this is really just very difficult work to do. But it is the gold standard method for looking at sediment production on hill slopes. It's cheap and simple in terms of the idea and the methods, but it's not so cheap in terms of the labor you need to do that. And it's going to typically be used at an event scale, what happened in an individual storm or over a few weeks. I mean, to use that on an annual basis, you'd have to have relatively low sediment fluxes taking place. The simple approach, for looking at both erosion and deposition is to just put out a stake or have a benchmark on the ground or something. It's not particularly satisfactory, although it is the most simple approach. And the reason it's not satisfactory is that stakes can fall over. They can create their own local hydraulics and scour deposition patterns. So they're basically disturbing the flow and sediment regime potentially. But still, they're really inexpensive. They can work well in a very low energy environment. You could also see them used on like a cut bank. So if you have a river and you have a very steep bank, sometimes people will put pins into the bank to see how that's changing. So it's a very simple go-to method where you have to size the stake. It could be a long nail. It could be a meter stick. I mean, it could be a variety of things. But in general, people have moved away from this because you just encounter a lot of practical problems in their implementation that's led to more sophisticated technologies. And one of those that's used in a depositional environment quite a lot is called the Sedimentation Erosion Table. It's essentially a stake-based approach, but you don't leave the stake there when things are happening. So what happens is you go near to the spot you'd like to make a measurement, and you take out a core and you put in a pipe. So without worrying about that part of it, but you put in a pipe, and that bottom of the pipe is the reference elevation that, if the ground under that is swelling or shrinking or something, then the whole thing is going to be moving with that. But by putting that in as far as you can, in this case recommending 3 to 6 meters, then you're establishing a pretty big range over which you're evaluating change compared to your underlying benchmark. So you put that in, but that stake is not where you're actually measuring the sediment. Instead, you have a removable swing arm, which is shown on here, and when you want to make a measurement, you put this arm on top of it, and at the end of this is a flat square plate with many pins in it. And a photo is worth 1,000 words here. So here's an example on the left and as well on the right. But you've got this swing arm, it's got this metal plate, and then here there's a series of 9 long pins that are going down. And instead of measuring the height of the pins above the bed, we're typically measuring the height of the pins above this plate just for simplicity, and then converting that. So you basically can average across all of these elevations and then do this repeatedly, like, come back once a month or once a year and put this whole swing arm on, make the measurement, take it off, and go away. So that way natural processes can be taken place, and then you put the set in and make your measurements. So the main advantage here is you're allowing processes to take place without disturbing them or influencing them. The disadvantage are, of course, it's really expensive to put this in. You don't have to leave the swing arm out, but you have to have one of those, and you have to put in all the pipes and everything else. Another factor is that just scientifically, it's measuring change in elevation. And change in elevation isn't just due to erosion and deposition. It's caused also by swelling and shrinking over this full range that is represented. So unless the swelling and shrinking also causes the reference to move, then you don't know. And then, of course, if you're interested in millimeter scale changes, any amount of variability, any flex or pinning this in, just the slightest differences of any kind can cause changes here that would be within the uncertainty that's there. A common thing here is to put a marker horizon. I'm going to talk about that in a moment, so let's not worry about that right now. Another technology that you see, especially in more erosive, aggressive settings, especially gravel bed, cobble bed rivers, is something called a scour chain. So the scour chain, you take this chain and you insert it into the bed vertically. I'll talk in a minute about how you do that, so let's not worry about it. You have the chain, and so it's like flush with the surface. And then when scour takes place during a flood, then it exposes lengths of the chain. So if you know the total length of the chain and then how much is exposed, then you can know how much eroded through time. Another variation of this is to have a string or metal cable that has beads or wiffle ball kind of like things on it. And so when it erodes, then the wiffle ball launches. What's nice about that is that if you then get deposition on top of it, you do not only do you have the shape of the arc that's there, but you also have the fact with these wiffle balls that they're going to be retained there. So here you can see like the multiple processes of erosion where like the scour chain is always going to be at the position of deepest fill, but the wiffle balls have the opportunity to like float back up and basically adjust themselves as you have different erosion and deposition taking place to stay on the surface. So you know that they've launched. You can't unlaunch a ball, but in terms of where it's located will be different than the scour chain. Here's some just different types of scour chains, and typically what happens is you have a hard point at the bottom because you got to push this through gravel and cobble, and so that typically is going to be in a pipe. There's different ways of doing this, but it's possible to just have a pipe and the point, pound that down, and then load up the wiffle balls onto the thing afterwards, or you're just pounding it down with the chain links that are already there. These can have different lengths. They can have different chain lengths, link lengths. Here's a photo of us installing one of these devices here in California. And you could see the pipe that's used. We have a sledgehammer, and you just have to pound that as hard as you can, either breaking grains or working your way around them to get into the bed, and then loading in the little wiffle balls in there. I also want to say that they also have electronic versions of these where it actually records when a wiffle ball, I can't remember if it's when it launches or when it gets to the end, probably when it launches, but it basically can electronically detect the event of the wiffle ball moving, and then you can have kind of like a rate of scour rather than just the overall scour. Because you have to go back out manually and then count those links or wiffle balls. So that's giving you the overall change in elevation from the time that you first put it out to the time you go and check on it. If you have electronic observation, then you can see the intensity through the events. The next thing is called the net sedimentation tile. This is a little bit like the SET in that you have a vertical rod that you pound into the ground, and that creates a baseline from which you then are measuring. But instead of having the arm that you take away and bring back, and then having to independently get a sample somehow, the net sedimentation tile caps the stake with an 8-inch by 8-inch, or whatever size you want, ceramic tile. And that tile is glued to a piece of plastic and vertical plastic tubing, so that tubing can just go right on the stake, and it's capping like a graduation cap. And so that's flush with the ground surface, and then material can come and go. You can have erosion, but the erosion is not heavily influenced by the tile because the pole is far away from the edge of the tile. So you measure erosion by measuring with a ruler the height that the tile is above the ground in 4 positions, 1 on each side, or using the 4 corners. And so that's a little bit like SAT because you're making 4 measurements instead of 9, but it's still measurements away from the stake. But one benefit of the tile is it's giving you the material so that you can actually get the mass flux rate, and it allows you to do both deposition and erosion. The solution to that with the SET is to have a marker horizon, and I will talk about those marker horizons in a moment, but it's not quite as good because you have to core through that as opposed to just being able to sample the tile and then put the tile back. Now you can imagine that if you're progressively filling sediment up, then the tile is going to be, when you take the sediment off, it's going to be lower than the ground surface. But that's easy to fix by simply putting a block of stuff inside this tube, which then raises the tile up to keep it flush with the surface. So you can maintain its position at the surface even as the surface is going up and down through time. And here's just a photo of that tile in the lab, and then an example of a very aggressive deposition on a floodplain where we actually had to use a metal detector to find this electrical conduit and put it in. And the other thing is too, this is dramatically less expensive to construct and implement compared to the SET. Another thing is to just build a trap. So whether you're in a stream or a hillside, you can dig a hole and either just line that with an appropriate liner, or put in a 55-gallon drum, or cut half a 55-gallon drum, and then as water goes through there, then it collects. I mean, you'll even see in a river where you're interested in like a debris torrent or bedload material. If it's a small enough stream, you could do like a V-notch weir installation with a trap upstream of that, because you're going to have like a pond there, so you can collect all of the material as well as record the discharge. It's just very labor expensive. Again, anytime you're collecting large amounts of material, it creates a lot of work to do. And then you can have an oceanographic sediment trap. This is intended to catch particles that are settling down through the water column. And so it's kind of like a tipping bucket rain gauge. There's a funnel on the top of this thing, and sediment is funneled into there and goes into the trap. So it's a little bit different, but if you're working in an estuary or a lake, then that kind of technology could be useful to you. Next is bedload traps and samplers. So what's bedload? Well, material that's moving in a river can be suspended in the water column, or it can be rolling and tumbling along the bed. And we have to sample those in different ways. Haven't really talked, I guess, about suspended sediment, but of course you could imagine you can just take a bottle and put it into the river and grab it. You can suck it out with a tube and a pump, or with suspended sediment. What was the other one? Oh yeah, well there are like dedicated suspended sediment samplers. So I'm not covering that right now, but I did want to mention bedload in particular because it's a little bit more tricky to do, and we're talking about what's going on the surface more than the flux in the water column, and we will be getting to that when we talk about water quality and turbidity and so forth. But bedload usually is not part of water quality. That's why I'm covering it here. So with the bedload trap, you want to have some kind of device that's sitting on the bed that the material is going to go into. And here's just simple examples of a trap that it's going into. Here's one that is a metal device with a net behind it, and so all of the material goes into the net. And there's also one that's pretty big called a Heli-Smith sampler. It's hard to get a sense of the size here, but it's this big metal frame, and then you have a sample bag. And I just want to show you some movies that will illustrate how this works. So here's a YouTube video showing bedload sampling during a fairly sizable flood. And let's see, don't want to go full screen, but I mean, just look at how challenging this is to be driving this really small boat in a flood, and look at the size of that Heli-Smith sampler. I mean, it's bigger than this guy. And look at the large amount of material that's being collected in there. So it's very challenging to work with this kind of sampler. I also just want to show you another video that shows bedload moving in the river and what that looks like. So this is another Heli-Smith sampler video, this time being launched off like a cataract with some video cameras. You can see the suspended material, both organic and inorganic material that's moving through there. And you'll also see that there are particles moving along the bed. Some of this is suspended sand, but some of it also is there it goes, like rolling and tumbling. And so you leave this Heli-Smith sampler on the bed and wait for particles to hopefully roll into it, not just by it. And so that gives you a sense of what bedload looks like and how you collect it with a bedload sampler. Just fast forward this in case anything exciting happens. Well, probably not. Yeah. Okay, so that's a bedload trap and sampler. Another thing you can do, which is a little bit like the Scour chains, is to use what are called tracer particles. And we're going to have a whole presentation coming up in water quality about environmental tracers. But this is specifically for surface material. So in this case, we took a McNeil core and we cored out the material in the bed. But then instead of leaving a hole, we took that material, dried it out, painted it, put it all back. And we did it in 4 ways. We have one with a mix of sizes, and then 3 with different grain, isolated grain sizes. And so as scour is taking place, not only can you see how much material is leaving from your tracer pile, but then you can go down the river and try to find it and see where those particles went. And that will tell you something about the sediment transport regime and conditions, hydraulics, that were responsible for that movement. Of course, the biggest challenge is you can have 1,000 particles going down the river, and you'll be lucky to find 10 or 20 of them. It can be really challenging. So this works better in smaller streams than bigger ones. Okay, I promised I'd cover the marker horizon. So a Feldspar marker horizon is basically like a chalk or a very fine clay cohesive material. You put it out on the ground. And when the ground is, you're putting it on the surface basically, and then over time, if you're in a depositional environment, then you'll get a deposit on top of that. You might wait a year, you might wait 20 years. This is a variety of things. Generally, a very long time for marker horizon, and then you come back with preferably some liquid nitrogen. And you take a sediment core. Notice here's an SET, and they're using some liquid nitrogen. You're making a little dirtsicle here by freezing the sediment, and then it's like dirt on a stick. And you can see the they just put the stick in the ground. They froze around it, and then here's the frozen water. Here's the frozen sediment, and there's the Feldspar. And they can just use a caliper to measure how much deposition was there. But So this does give you a sediment sample. It's just that the frequency of this collection is going to be relatively infrequent, like I said, and this is for low energy environments that are net depositional. Well, not just net, but are just exclusively depositional. The net sedimentation tile is superior because it can handle both erosion and deposition because you're putting in that fixed element. Okay, well the next thing, which is pretty important, is instead of actually trying to get material or just look at depth changes, would be to map the whole volume of change. So how much is a river or an estuary or a reservoir or even a hillside? How much is it changing? And like if you have a big gully or you have a river that's meandering or incising, then you'd like to do this. And the approach is to go out with the surveying technologies that I talked about earlier in the course, map the land, and then come back after enough change has happened and remap the land. If you only have a couple centimeters of change, you're not going to be able to resolve that with this technique. You have to have enough change that you can capture that by surveying. And here's a flood that we observed. It was a pretty large event that took place. It was like a once in 20 to 25 year event. And this is a map of this area. I mean, you can kind of get a sense of the scale here. I mean, the width of this thing is like, what, 300 or 400 feet wide. So maybe, 1,000 feet long. And what's shown here is the net change. So if I take the topography at time 2 and subtract from that the topography at time 1, and that's all GIS, and don't worry about that right now, but what you can see is the areas in red are areas of scour and blue is areas of fill, and the intensity of that color is proportional to the magnitude of that scour or fill. So you can see where the river was located. It actually scoured out a side channel on this side, and meanwhile, a lot of material got deposited in the channel where this blue is. So there's a lot of processes that are going on in that, but just seeing the volumetric change of topography is a very powerful tool for understanding erosion and deposition. And then the very last thing is when you have a large vegetated floodplain, and you're going to have a lot of fine-grained deposition, you can use a method to look at tree burial. And you have to collaborate with somebody or know how to do what's called Dendrochronology, which is figuring out how old a tree is. But typically, you can core into the tree with a borer and count the tree rings and get how many years that the tree was there. And then trees have something called the flare root, and that flare root is the base of the tree at the time it was established. So then you just basically dig from the surface down to the flare root and measure that height. So in this case, let's say you had 10 centimeters of sediment accumulated above those roots, and the tree was 20 years old, then you would have half a centimeter per year of deposition. So it's almost like a Feldspar marker. I mean, you're not there on day 1. So this is a historical approach that you can see how much has changed over the life of trees in the forest, and that can be very powerful as well. So that's kind of a blitz through a variety of methods for measuring deposition and erosion related to surface sediment characteristics, whether you're on the terrestrial ground or the submerged riverbed or estuarine bed. These kinds of measurements are very important in terms of understanding the mechanisms of how water, sediment, and biological materials are flowing through. And so these are the kinds of measurements that I want you to see in class. And we'll be playing with several of these in our labs and field trips in the upcoming days.